Graphing. I mean, everyone's pretty much must have taken some sort of class in the past, like biology or chemistry or even like geography, where you're given some data and you got to figure out what's the relationship between this group of data and this group of data. Are they related? Are they not related? The way we do that is by looking at them in a sort of picture representation, because our eyes are really, really good at seeing patterns. What they're not so great at is being able to determine whether those patterns are significant or not. And so we need to actually use some, I hate to say this, mathematical tools to see whether or not the relationship between data is actually real, or whether it's just looks like it is. And there's a really good example a little bit later. So we're going to be looking at the growth of plants over time. And so we have a couple of different variables. Experiments always have variables in them. One of them is a dependent variable, and one of them is an independent variable. Anyone tell me what the difference is between a dependent and an independent variable? Just shout it out.
Independent is something that an experimenter has control over. However, the dependent one can be changed, and which can be based on the independent variable.
So which one can be changed?
The dependent.
The dependent variable can be changed. So who changes it? The experimenter?
Yes.
Okay. So that is the sort of the confusing part about the way that we name these things, because it does sound that way, right? It sounds like a dependent variable is something that depends on us varying it. But in fact, it's exactly the opposite. It's the independent variable that we can vary. And it's the dependent variable that's actually dependent on the independent variable. So we can change the independent variable. Like for instance, if I'm doing an experiment and I'm testing doses of different high blood pressure medications, for instance, let's say. So I've got a low dose, a medium dose, and a high dose. I decide what those doses are, and I decide who gets them. So that is an independent variable because I decided what the doses were. Now the dependent, what would the dependent variable be in an experiment where I'm looking at high blood pressure medication? So the independent variable is the dose. What would the dependent variable be?
The blood pressure.
Exactly. I have no control over that. I have no control over the blood pressure. The blood pressure of those patients is dependent, I hope, on the dose of the drugs I gave them. So that would be the dependent variable. Right. So it is a little confusing. I was always confused with this at first too, because it seems to be the opposite. But the way to think about it is that I can independently vary the independent variable, but the dependent variable, it is dependent on whatever I choose the independent variable to be. So that's where the real meaning of the terms independent and dependent come from. So if we're going to plot these things, if we're going to make a graph, let's go to the next. So if we're going to draw a graph, so I draw my two lines here. Which one is the x-axis and which one is the y-axis? Couldn't hear you, sorry. Which one is the x, which one is the y?
Y is vertical, x is horizontal.
That's right, excellent. Right, so this is our y-axis over here. And this is our x-axis here. Now, which one would I put the dependent variable on?
X.
Now remember, X is the one that I can, dependent's the one I can, I sort of gave that away. X is the one I can vary, and Y is the one that changes as a result.
Y.
So X is independent and Y is dependent.
Exactly. So I can change X. So for instance, this would be my dosage here. So I would have my low dose, my medium dose, and my high dose. And the Y would be the blood pressure. And so basically then I would get data that looked something like this. Because these are people and not lab animals, there's all kinds of scatter. And we're going to talk about that in a minute as well. So I'd get data that looks something like this. I'd have one group with a low dose, one group with a medium dose, one group with a high dose. And I would see if there was a difference in those groups. If I was just doing a single experiment, then I would do my drawing like this. This is the sort of plot we're going to be doing tonight. So I have my X, I have my Y. Here's my points, and then I draw a straight line through them. What do we call the slope of the line? Anyone know what the equation is that you get when you draw a line like that?
Y equals mx plus b.
There you go. Man, you were all over this. Excellent. Yeah, we get Y equals mx plus b. So what is the m?
The slope.
The slope of the line. That's right. And the slope of the line is defined as what's the change in Y. And in science, we show change as delta. What's the change in Y over the change in X? That equals the slope. So the slope tells us basically what is the relationship between X and Y. If Y changes by 2 every time we change X by 1, then our slope would be 2. And so that would mean Y is equal to 2X or 4X or 6X or whatever the relationship is. What's this plus B thing? We're gonna have to deal with that tonight. What's the plus B?
The
Is it the
y-intercept.
y-intercept?
The y-intercept, that's right. And what does that mean exactly, the y-intercept? Because that's something we're going to be doing tonight. We're going to be focused on that pretty clearly. What is a y-intercept? Where would I find the y-intercept on this, for instance?
The y-axis.
On the y-axis. So where on the y-axis? Here?
0, 0, 0.
Is it always 0?
No.
No.
That's right. So the y-intercept is actually where the line crosses the y-axis. So here, it seems to cross it right about there, very close to 0, but not precisely, it seems. So when X equals 0, this plus B or the y-intercept is whatever the value of Y is at that point. So most of the time, we kind of want the y-axis to be 0 if we're starting from 0. Like for instance, if I was plotting mass versus volume or something, and I wanted to see, because I wanted to see what the density of metal was. So I was measuring the volumes and the mass of different pieces of metal. Well, at 0 mass, there really shouldn't be any volume, right? They should both be 0 at that point. So if I drew my line, and my y-intercept was not 0, then I'd sort of be scratching my head saying there's something, maybe I did something wrong with that, or maybe this line isn't the best way to represent my data. So we're going to be doing that. This is the basic graph we're going to be doing tonight, trying to visually represent the data and see what's the relationship between X and Y, and seeing where it crosses the y-intercept, and then trying to figure out where should it cross the y-intercept. Need to clear the drawings. So here's the data we're going to be using. So this is from, hopefully everyone's seen the instructions. Has everyone downloaded the instructions, hopefully? Crossing fingers, hoping that's true. So this is the first data that you get, and it basically just gives you 6 different plants. 3 of them are wheat plants. Oops, let me go back. 3 of them are wheat plants. So we got 3 wheat plants here, and we've got 3 rye plants over here. So basically what we're thinking is, in an experiment like this, we're probably treating those plants differently. Like maybe we're changing the fertilizer we're using, or maybe they're getting different amounts of light, or maybe they're getting different amounts of water. We're doing something to them that make them different. And we want to see whether that difference can be seen, and whether that difference is statistically important. And so we're looking at the growth of them in centimeters. So we're looking at their height. We're measuring the height in centimeters, and we're measuring that height every week. So in this experiment, which one is the dependent variable and which one's the independent variable?
Would the independent variable be like the type of plant? Like the wheat and rye plant?
But we're not going to be plotting those, are we? We're not going to be plotting wheat plant 1, 2, and 3. That's actually, so that's a source of the data, but it's not the data itself. The data itself is right here. This is the data itself, right here. So what are we going to be plotting on the x-axis?
The height and the weeks.
Sorry?
So the height depends on the weeks.
That's right. The height depends on the weeks. That's exactly right. So which one is our independent variable that goes on the x-axis?
The weeks.
The weeks. Excellent. That's right. Because we get to pick when we measure them. It could be twice a week. It could be once a week. It could be 5 times a week, or once a month. We're deciding, and obviously that's going to affect the change in height. If we measure it every day, the difference in height's not going to be that much. If we measure it every week, it'll be a little bit more. And if we measure it every month, it'd be a really big difference. So the dependent variable is the height, and that will go on the y-axis. And then basically what we're going to see is we're going to look at the data when we plot it and see, is there a difference between 1, 2, and 3? And we might also want to look, is there a difference between the growth of the wheat plants and the growth of the rye plants? So one of the things that we're going to look at in terms of whether or not our data is any good, or whether it's representative of a larger group, is not only do we want to know what the averages are. So up here we have an indication. It keeps doing that. Up here we have an indication of an average. So those are the results of the 3 wheat plants at the end of the experiment. One was 10 centimeters, another one was 10 centimeters, and another one was 7 centimeters. So the average was 9. So one of the questions we want to ask us is that 7 like really out there? Should the average be 10 rather than 9? Is there a mistake in including that plant that only grew to 7? Or if I grew 1,000 plants, would I expect a lot of them to be around 7? Because any of you who've worked in the hospital or in the healthcare field No, that not every patient is exactly the same, right? I mean, that's, believe me, working in a clinical lab for 10 years, you get a lot of deviation that you can't control. You can't control, what your patients eat, although you want to. You can't control what your patients eat. You can't control if they smoke or not. You can't control if they get a certain amount of sleep. You can't control the neighborhood that they live in. Is there certain toxins in that environment? That all of these things are going to affect your experiment and your treatment of them. What you want to know is, are they outside of what I would expect those results to deviate? So we collect something called the standard deviation. What that means is, how much does my result differ from the average? So the way that we calculate that is we get the average, and the average, calculating the average is pretty straightforward, right? You just add everything together and then divide by the number of measurements. So that part is easy. Then the next thing you want to do is calculate the difference between each one of those numbers, each one of my results, and what the average was. So in this case, it would be, the average is 9. And so one of them is 10. So the difference is -1. Another one is 10. So the difference is -1. And another one is 7. So that difference is 2. So then we square them. So that is 1, 1, and 4. And then we take the average of these. So 1, 1, and 4, that's 6. That averages out to 2. Then we take the square root of that. Square root of 2 is around 1.4 or so. And so what we say is our standard deviation, and that is given this symbol here, is around 1.4. So what that means is that about 2/3 of the time, we would expect our average, any one of our data, to be within 1.4 of our average. So if our average is 9 centimeters, if I grew 1,000 plants, I would expect about 680 of them or so to be within 1.4 centimeters of 9. That's expected. That's not a big deal. I would expect 95% of them to be within 2 standard deviations, which is 2.8. And that's where the 7 comes in. 7 is within 2 standard deviations. Anything outside of that, I'm probably not looking at the same population. So as scientists, we want to look at the within 2 standard deviations of the mean. So our mean here is 9. And like about 2/3 of the time, they're going to be within 1 standard deviation of that. And 95% of the time, it's going to be within 2 standard deviations of that. Anyone who's listened to polling data, and you probably get, whenever there's an election around, everyone gets tired of listening to polling data, right? I mean, I know I do. But when they tell you something like the Republican in a particular riding has 46% of the vote, plus or minus 2, 19 times out of 20. Now, most people don't know what the hell that means. They just say, oh, they got 46%. What that means is that they interviewed, I don't know how many people that they called on the phone, but the average of what they saw of who were voting for the Republican was 46%. So this is our 46% right here. Plus or minus 2 is 1 standard deviation. So there is plus or minus 2. And the 19 times out of 20 refers to this, that they would expect that result to be within 2 standard deviations, or plus or minus 4, 95% of the time. So when you hear that on the radio or the TV or the YouTube video or anything, it sounds confusing, but this is what they're talking about. So we're going to do, there is going to be a question about calculating standard deviation in the instructions. I am not going to ask you to calculate standard deviation during a test or anything, because it is so easy to calculate standard deviation either on a scientific calculator or on your computer. Just Google standard deviation, you put in all your numbers and it'll just spit it out for you. So it's important for you to know what standard deviation is, not so important for you to be able to calculate it, because this is something that a computer was built to do. All right. So this just basically goes over exactly what I just said. This is table 2 from the instructions, and it just goes to show you what the average is, what the difference from the average is. That's called the variance, and we're going to talk about that a little while later. And then the standard deviation is just the square root of the variance. So it just basically shows you how you would do those calculations, but don't do them. Get a computer to do them for you. Much easier. So this sort of relates to just what I was telling you about earlier. When you're getting this sort of information, either in the press or on YouTube or even in a scientific article, you will get data presented that looks something like this. And so here there's 4 different groups they're looking at. There's group 1, group 2, group A, and group B. Now, basically what they want to find out is there a statistical significant difference between group 1 and group 2 and group A and group B? Now, looking at them, which of those 2 would you say are different? Group 1 and group 2 or group A and group B?
1 and 2.
Clearly, right? I mean, if you look at that data, the way it's presented, there's clearly a difference. The average of group 1 is 20 years. The average of group 2 is 40 years. That's twice as much. That's got to be different, right? And then when you look at group A, the average of group A is around 28, maybe. And the difference in group B looks to be around 34, which is pretty close. So yeah, I think anybody would look at that data, the way that it's presented, and say, yeah, clearly there's a difference between group 1 and group 2. But this is a lousy way to present this data, because all it does, these bars don't give a clear indication of what that data actually looks like. What they really should plot is all the data so we can get to see it for ourselves. And that's what we've got on the next page. So if we look on the next page, if we look at all the data points, then it's a little bit of a different situation. Because now we can see that there's a huge amount of scatter in these data. Group 1 and group 2, you can see that group 1, you remember the average age was around 20, and group 2, the average age was around 40. Well, in group 1, that also indicated someone who was 80, somebody who was 40. Group 2, someone who's 90, a bunch of people who are 10. And group 1 has a whole bunch of people who are actually less than 10 years old. In fact, most of them are less than 10 years old. So in fact, the average might not be the best way to represent that data. I would say that you would probably want to represent it with something like a median. Anyone know what a median is? Anyone taking statistics?
It's just the
The
middle
middle number.
group.
It's what?
It's just
The
the middle
middle.
number of the-
It's
of
the
the-
middle, right? But it's not the mean. The mean is the average. The median is not the average. What the median is, it's a value that half of the data points are above and half the data points are below. And so why that is helpful is that if you have like really crazy data like we do here, with most of group 1 being less than 10 years old, but some of them being 80. So when you add, 3 people who are like 5 years old and someone who's 80, then the average is like, 35. Well, that doesn't make any sense at all. The median would be about here. The median would be around 10. Because looks like about half the people are below 10 and the other half are above 10. And the same with group 2. It looks to be maybe, well, group 2 is hard to say anything about group 2 because it's really all over the place. So if you were to put error bars on them, you would see that there's a huge amount of overlap. So if we look at figure 3 here, we see there's a huge amount of overlap between group 1 and group 2. All this space they have in common. So we can't really say that there's any statistical difference between group 1 and group 2. On the other hand, let's look at group A and group B. So group A and group B, if I drew a line right about there, you can see with group A, there's only one patient, or whoever this is, one patient above it, and everyone else is below it. And in group B, there's no one below it. So these two groups are actually statistically different. So it doesn't look like that if we just look at a data set that looks like this, or if we don't have the error bars on it. If we just look at the averages, we really wouldn't know. But we see that group A is very, very similar. They're all similar to each other. Group B, they're all similar to each other, and they're different. Even though that difference is small, it is significant. And so, like, working in a lab, I can tell you this is what working with human subjects looks like, and this is what working with lab rats looks like, because there is really no difference when you're looking at two populations of lab rats, except the dependent or the independent variable. They're all exactly the same size. They all have exactly the same genetics. They're all fed exactly the same thing at exactly the same time and sleep exactly the same amount. They're completely identical in every single way. So basically, anything you do to them, you're going to see a difference that's significant. But with people are troublesome. So people, you get data like this, and it's hard to make hide in their hair what's going on with them. So you always have to look more closely at your data to see if it's really telling you what you think it's telling you. All right, so the first thing we're going to do is graph by hand. So we're going to draw a couple of graphs by hand. We're going to draw the wheat plants, all three in one plot, and then the rye plants, three of them on one plot. So on page 13 of the instructions, they basically give you some graphing paper. You don't have to use those. If you can't print them out, that's fine. If you have a notebook that has like the crosshatches already on it, like a graphing notebook, just use that. If you don't have that, you can just like draw the crosshatches on your right on the page and plot it on there. Just do it neatly. So it's really important to do it neatly. So the first graph will just be wheat plants, height by week. Second one, rye plants, height by week. And then we know the x-axis is going to be weeks. The y-axis is going to be height. And what's another important thing here is that you, on any graph you do, there's certain things that have to be there. So let me go through what I'm talking about. Got a fly in here. Ugh. So here's my graph that I'm going to draw. Here's my time. And here is the height. So some things you want to do. Always make sure that you have units present. If I just have height and time, I don't know what that means. The height in what? Feet, inches, centimeters, yards, miles. I don't know what you're measuring in. So in brackets, we put centimeters. And time, again, I don't know what that is. Seconds, weeks, months, years, I don't know. So brackets, weeks. Always have units on your axes, because that's the only way I'm going to know exactly what it is I'm looking at. The other thing, you pretty much always want to start at 0 unless you have, negative on your particular independent variable. I don't know what that might be, but sometimes you do. And then the other thing, if you want to use the whole space of the graph. So if my graph is this big, I want to have data filling up the whole thing. I don't want to have all my data down here and a line, and then the rest of it is blank, because then it's really, really hard to see what kind of job you've done. So you want to have the maximum height to be about here, and you want to have the maximum time to be about there. That way you fill in nicely the whole area with your data. So don't just squeeze it all into one group. The other thing that may seem obvious, but it isn't sometimes, is there has to be a regular difference on the time. I can't have 1, 2, 4, 8, 15, 26. Obviously, it's got to go by ones or by twos or by halves. It has to be regular, both on the x-axis and the y-axis. The other thing to think about is if you're plotting more than one thing on this graph, and that's what we're going to be doing, right? We're going to be plotting 3 different plants. You want to have your data look different, so I automatically know which plant it is you're talking about. So like a diamond for plant 1, or a square for plant 2, or a cross for plant 3, or an X, or a dot, or different colors is really nice. If you can draw in different colors, that's even the best way. If you're just doing black and white, then try and make them different figures. Okay, so it's pretty easy to tell which is which. The other thing then, if you are plotting 3 or 4 or 5 different things on the same plot, I need to know what they are. So you need to have something to tell me that this means plant 1, and this means plant 2, and that means plant 3. So you've got to have that. We call that like a key. That's got to be somewhere on the graph so that I know what I'm looking at. Okay. So when you're done, you should have something that looks like that, right? So you can see that this has pretty much everything we're looking for. We have a key down here that tells us what the different points are for each plant. Okay, that's cool. We know what the time is. Didn't really have to go to 14, probably could have just gone out to like 12 maybe. Just made it this big. Use a little bit more of the space, but it's clear what the units are. It's clear what the data is. It's clear which plants they're talking about. That's everything we're looking for. So now all you need to do is figure out what is the best fit line to put through them. So let's look at plant 1. So that is this one here. So here's the data. So it's 1, 2, 3, 4, 5, 6, 7, 8. So it's those. So you're obviously not going to be able to draw a line that goes completely through each one of them. If the world was perfect and you did a perfect experiment, you would be able to do that. So what you want to do is get a ruler and try and draw a line through it that is as close to most of the points as you can. So it'd probably be something like this. So that's pretty close to all of the points. You want to have some that are a little below the line and some that are a little above the line. If all the points are above the line, then move the line up. So this one, it goes through some of the points exactly. Some of them are a little below, some of them are a little below. I'd say that's a good fit. Okay. So any questions about drawing these things by hand? So that's basically the first two things to do in the lab tonight. It's just take the data from the instructions and then do this particular plot. So is everyone clear on that one?
Do we have to draw a line for each one? Like for the triangles, draw another line?
Yep.
Okay,
Yep. Yep.
thank you.
Yeah, because what we want to do, because the next thing we're going to do is actually plot them with the computer. And we want to see if the line we drew is anything like the line the computer would draw. So I'm just kind of curious to see how you would draw the line. I would kind of like to know if you've done this sort of thing before. What kind of line would you draw? Because then when you see what the computer draws, you'll see that, well, yeah, I pretty much drew it the same way, or man, that is completely different than what I would have done. Any other questions? Because I'm just gonna go to the computer part next. Okay.
I have a
Oh,
question.
sure.
When in regards to drawing the line, does
Mhm.
everything has to start with a 0?
Ah, excellent catch. No, because I didn't take a data point at time 0, did I? I didn't. So I can't put a piece of data there. So that's an excellent point though, because that goes to what we're going to be doing next. So I can't really do that because that's not part of the data here. So my y-intercept is slightly above 1, like say b would equal around 1.2 or so. But that's an excellent point, because if it was a perfect experiment, it should go through 0, right? Because this is basically time after planting a seed. Well, when I put a seed in the ground, do I have any height? No. At that exact point, when I start, like seed goes in the ground, start the clock, there's no plant. So there should be 0, but we didn't take that. We didn't put that point there. So I can't really in good conscience draw a line through it. But that's an excellent point, because that is the correction we're going to be doing the second half when we actually do the computer. Because after you draw these two graphs, the second part of the report you're going to do is looking at the slope that the computer plots, excuse me, without correcting for an intercept of 0 and with correcting for an intercept of 0. And we'll see we're going to get different results. Great question. And just lead right into it. Captain Segue. So there's two different ways you can use, or two different softwares you can use for doing this. Excuse me, man. So one of them is Excel, and Microsoft Excel is a real pain to use. Some of you may be experts at Excel. I've been using Excel for like 30 years and I still don't know how to use it. So it's not my favorite. So what I was going to do is actually show you how to do the computer graphing on Google Sheets, because everyone's got access to Google Sheets. You may or may not have Excel. If you do have Excel and you prefer using that, then by all means use that. But I just find it a lot more difficult to use. I embarrass myself when I try and demonstrate how to use it, because it usually takes, even when I've done it perfectly, like 10 minutes before, trying to recreate that I just find difficult. So I'm going to take you through Google Sheets. I even posted a video in Canvas about how to do this. So that will be available to you as well as recording of what we're doing now. So we're gonna go to Google Sheets and basically we'll take you through how to do that, okay? So let me stop that share and start a new one. Don't want that. Okay, so you should be able to see my screen here, right? Hopefully, can you see the screen?
Yes.
See it?
Yes.
Okay, excellent. All right, so where is, no, let me move that. All right, so here is my spreadsheet. So what I've done, we're just going to do the wheat. Okay, we're just going to be looking at the wheat. So I'll show you how we. So this, I just typed this in. Let's do a quick copy and paste. All right. So here's my data. So I've got my weeks, plant 1, plant 2, plant 3 in different columns. So next I want to make a plot, right? So I just select my data. I go up to insert. Oh, did I show you how to get here? That might be a good idea. So you go to Google. So I'm at google.com. I come over here to Google Apps and I scroll down to, where are Sheets? Docs, Sheets, there it is. And then I just say, start a new blank spreadsheet. Okay, so that's how you get started. So here I've got my data and I want to make a plot. So I go to insert a chart. I want a chart. And it'll basically say, well, what kind of chart do you want? And it suggests a scatter chart, which is perfect because that's exactly what I want. So the other things it has are line plots, which I'm not particularly interested in because I want to be able to see each data point. And the way to see each data point is what's called a scatter plot. So you want to select a scatter chart, okay? So now I can double click on pretty much anything here and change it. So for instance, if I were going to include, so in future experiments, you're going to want to include a data chart with your report. So here you can see it automatically gives you a key, it gives you a title, it gives the representation of the x-axis. The first column is always going to be an x-axis, right? So you always want to have your x-axis to be the first one. And then any subsequent, so the independent variable always goes first. So this is my independent variable. I put that in the first column. And then I can put as many dependent variables as I want. I can put 50 of them if I want. It may get a little crowded, but and then I just put them after, okay? So I'll make this a little bit bigger. I could make this a little bit taller. Instead of 10, I can vertical axis, maximum value. Let's say make it 11 so I can see it all. There you go. So now I can see all the data a little bit better. And the minimum I'm going to make like -1 so I can actually see. Now I can see all the data. I can see all of them there. So great. So I've got a representation here. But what I really came to do was to get the computer to draw straight lines for me. And so we do that by just clicking right on the data itself. So I'll do a click right on the data itself. Whoops, not that. I want Come on. There we go. So chart editor pops up and I want a trend line. A trend line is the computer is going to try and fit that data to a particular equation. What kind of equation do you want? Well, I want a linear equation. I want a y equals mx plus b. I could have a whole bunch of different ones here. I could set it to a logarithmic scale or a polynomial or a exponential, but I just want a simple linear line, the best fit line it can make. I go down a little bit further. How do I want to know what the equation is? So I click on label and I say use equation. And you can see right there popped up in the key what the equation is. So let me draw on that to make it a little easier to see. So right here, it has popped in what the best fit equation it could think of for those lines. Now, the next thing you want to do is show R squared right here. Anyone know what that is? R squared? Has anyone taken statistics before? If you don't, it's fine. I'm going to talk about it in a minute. But basically, what that is, it's called a linear regression. Regression. Which is a fancy way of saying, how good a line is that? If it's a perfect line and every single point is right on the line, you get an R squared of 1. That means it's 100% perfect. Every single point is on that line. That line is a 100% perfect representation of that data. And whatever this equation is, explains your data 100%. Well, that never happens. So you're always going to have some scatter. It's going to be a few points above and a few points below. And the R squared, or the linear regression, basically calculates how much error is there in the data. And I'll show you how it does that in a minute. But it basically tells you, is this a good line? Or maybe you should be thinking about a different way of looking at your data. Maybe you do want a different equation other than linear. So basically what scientists look for is we want to look for something above 0.9 tells us that yes, linear is the best way to go. And something above 0.95 tells us that that is an excellent representation. That's basically the gold standard. If you are publishing papers, or you're writing to the government asking them for money, which I've done a lot of, you want to have the best data. You want to show them that you're a good scientist, right? So when you're showing your data, you want to have an R squared of like 0.95 or better, because nobody can argue with that. You can make whatever conclusion you want when you have data that's good, that's that good. And you can see that the R squared for this particular line is 0.98. That's excellent. So that is an excellent R squared. So that equation represents that data very, very well. So next, so that was plant number 1. So now we want to do plant number 2 as well. So we find plant number 2 data and we click on that. So plant 2, we want a trend line. We also want that to be linear. And we can change the color of the lines. We can make them thick, we can make them thin, we can do all kinds of different things here. But mostly all we're interested in right now is what's the slope, what's the y-intercept. So you can play around with like making it look really good. But for this particular report, all we're interested in is the slope. So show me the R squared and show me the equation. So there's the equation for plant 2. And then next I find plant 3, click on one of those lines. same thing. I want a trend line. I want it to be linear. I want to see how good that fit is. And I want to see what the equation is. So here we go. So when we look over here, I've got my 3 plants. Here they are here. And I've got 3 different equations. So I've got, this is plant 1, plant 2, plant 3. So you can see plant 1 and 2, they're R squared, they're both excellent. And plant 3, not so good. Its R squared is 0.94. And if you look at the data, it's kind of obvious why that is. Because if you look at plant 3, look at these, the last 3 points from 6, 7, and 8 weeks. They're all the same height, right? They're all 7. And so one of those points is right on the line and the other 2 are off of it completely. So that is going to affect your R squared. The greater the distance from the point and the line, the lower your R squared score is going to be. So the other thing we're interested in, so this is the equations you will write down for uncorrected plant 1, plant 2, plant 3. Y equals mx plus b. Y is the height. M is 1.24 x. And then the plus b is plus 929. That is the y, that is the m, x, and that's the b. So that is the uncorrected equation. That's what you write down for the uncorrected equation. Now, the excellent point that was made before we did this is, how come we don't put the intercept at 0? We can do that. We can actually force the computer to draw that line so that it goes through the origin, which is when x is 0, y is 0. We can force it to do that. And that is what we call a corrected slope. Because when all we're going to get now, since b is going to be now equal to 0, since there's no y-intercept anymore, all we're going to get is y is equal to mx, because there's no b. So when we correct, there's only going to be a slope. There won't be any y-intercept. And I'm going to show you how to do that right now. All right, let's clear all this stuff. Now, this part's a little tricky, so I'll go through it kind of slow. The bizarre thing is, it's really easy to do it in Excel. You just click on a button that says, set the y-intercept to 0. The tricky part is trying to find that button. So that's why I'm going to do it here. So how we're going to do this is we're going to write basically a little script and telling the computer what it is exactly we want to do. So what we're going to do is write equals. So anyone who's worked with spreadsheets before, putting equals means you're going to put some sort of function in there, and then the computer is going to do the calculation for you in that particular box. So what I'm going to do is, it's called linist or linist, best fit linear trend, which is exactly what we've done here already. Each one of these lines is already a best fit linear trend, but I'm going to change it a little bit. So I put in a bracket, and first we put in our y data. So we have to tell it where our y data is. So I have to go over and physically click on the y data and then drag down to the end of it. So we're telling it the data I'm interested in fitting starts at C4 and then goes down to C11. That is all of my y data for that particular plant. Then I put a comma, and then I tell it where my x data is, and that's the week. And I just scroll all the way down and say that's where my x data is. Now make sure you get the same number of points. If you don't, it's going to screw things up. But you'll have like all week to practice. I also put like I said, I put a video in how to do this. So in case you don't understand what the hell I'm doing, maybe somebody else doing it can help too. So another comma, then interestingly enough, I write false, close bracket. Now, what does that mean? It means that the first slope you did, just letting the data go through any y-axis it wants, is false. I don't want that. I want the y-intercept to be 0. So when you do that, just hit enter, and it gives you the new slope, which is this. So this is plant 1. This will be plant 2. This will be plant 3. This is the new slope right here. And this is the new y-intercept. And you can see the new y-intercept is 0. So it basically drew a line and it forced that line to go through 0 and then fit everywhere else. And so you can see that the slope now is greater than it was before. So plant 1's initial slope was 1.24. So y equaled 1.24x. Basically, so every week, if x is weeks, it grew 1.24 centimeters. But we can see when we put it through 0, the slope's actually a little bit higher. Now it grew 1.4 centimeters every week, which is probably a little more accurate, since we know when we planted the seed, we started with a height of 0. So this is really probably closer to the real slope rather than this. Okay, so now we're going to, so this is the corrected equation. Y is equal to 1.40 times x. And there's no b because y-intercept is now 0. So let's do the same thing for the other two, so we can sort of see how we did that again. So how do we do that again? See if I can remember. So we want line estimate or linist. Oops, I forgot the equals. Got to put the equals in there. Equals linist brackets. Now I want to do plant 2. So remember, you want the y values for plant 2. Here are my y values for plant 2, comma. Here's my x values for plant 2, comma, false, closed brackets. Hit enter. Bingo. So you can see the slope for plant 2 is now also greater. And that makes sense, right? Since we're starting at a lower place. So our line should be tilted a little more than it was before. So that actually makes sense. And let's do it. And you can see that it's gone up by about 30%. It went from like around 1 to about 1.34. So that's a significant difference. So 3, let's do the same thing. So equal line estimate bracket. Here's my plant 3 y data, comma. Here's my plant 3 x data, and they're all the same, comma, false, close bracket. Now you can see with the third plant, our slope actually decreased a little bit. And that also makes sense, because if you look at what the y-intercept was before, that was the only plant, that was the only group of data that had a negative y-intercept. Right here, our negative, or the intercept was around 0.29. So it was negative. So now we increased it to 0. And so that actually flattens the line out just slightly. And so, but not by much. So you can see it didn't make a whole bunch of a difference. So it originally was growing at 1.04 centimeters per week. And now it's growing at 0.99 centimeters per week. Pretty much the same thing. So these are our corrected slopes. So that's your corrected equation. So anyone ever have any questions about how to do that? I sort of went through that rather quickly, because everyone's just sort of staring slack-jawed at how to do this. Has anyone used Google Sheets before? Is this the first time? Yes?
Yes, I have.
Yeah, it's pretty useful. It does a lot of the things that Excel does. Excel does a ton more, but I just find it much easier to use. Like when you click on things, things change. There's a lot fewer sub-menus and right clicks and all kinds of different stuff. So it's a little trickier to do this y-intercept business, but everything else is much easier to do. So any questions here before I sort of finish going through the instructions? So that is the second part, and that's pretty much it. You're done with the experiment. So let me show you. I just want to explain the fitting a little bit more. Oh, so this is the actual report template you're going to be using. Hopefully you found that in Canvas. So you just put your name and the date you're doing the report. That's fairly straightforward. So here you're going to insert. So you take your hand-drawn graph and like take a picture of it and convert it into like a PDF or whatever it is you want to do. Delete this. Delete all this stuff. And instead, paste a picture of your graph. Okay. I don't want to see like all the instructions still be here. Just put the picture of your graph in there. And then next describe the results of the experiment. Okay. Basically in your own words. Here we go. So that would be the wheat graphs. Next would be the rye graphs. And the same thing here. The data plotted, axis labels with units, title for the graph, a key, and then it asks you a question. If you wanted to compare the data, you want to compare the wheat data to the rye data, how would you do that? And sort of just basically just give me an indication of if you wanted to compare the two, how would you do it? What sort of plot would you do? Would you do a plot? Would you just look at the averages with some justification? Anytime I ask you a question and you just give me the answer, I would do this. That's not good enough. I would do this because I want you to explain anytime you just sort of answering a question, I want you to explain what it is that you're doing, okay, for the maximum score. So that is the first page. Second page is just the trend line equation, which is the linear equation you did on Google Sheets or Excel. What's the y plus mx plus b? And then the corrected one, which should just be y equals mx, okay? And then based on the corrected lines, which one grew the fastest? So what data would you look at to tell me that indication? How would you tell? And then finally, then you just have to answer the question why. And I put explain, I bolded explains. I really want you to explain. Why did we bother going through all that trouble of setting the y-intercept to 0? What difference does that make? Was that important? Did we really have to do that? Would that have changed anything if we didn't? And then finally, I just real briefly wanted to talk a little bit more about the R-squared, because that's something that you're going to be seeing every time you do a plot. You're going to be seeing that. So I just sort of wanted to let you know what that means exactly. All right. So this is what your scatter plots are going to look like. We sort of went through what we want them to look like. You want to use the whole space. You want to have axes. You want to have you want to make sure that there is units on the axes. You want to make sure you have your independent and dependent variables in the right place. Now, this is what the x squared or the r squared is going to be, how it's going to be determined. So when a computer is fitting a line, what basically it's doing, it is trying to minimize the distance between the line and the data points. So here are our data points. Oops, let me get a little bigger there. So here are our data points, and it wants, I want a different color than that. And so it wants to draw a line so that the distance between the line and the points are the smallest possible. So it's basically, it's minimizing the errors. And so what we say it's the best fit gives us the lowest value for distance between the points and the line. So when it's actually, so the other thing, so that's how it calculates the y equals mx plus b. It is trying to find what is the line that gives me the lowest value of the distances here. Now, next, when it's plotting the regression, it's doing it in the same way. Basically, we were showing how to calculate what the standard deviation is. That's what it's basically doing. It's looking and seeing what the standard deviation is between what the expected value should be. See, every one of these points is the expected value. When you use this equation for x, this is the expected value for y. And so it looks at, well, what are those variances? And then it squares those. It figures out what the standard deviation is. If you have no standard deviation at all, you have a perfect 100% correlation, and your r squared is 1. So that's basically all it's doing. So when you're actually hand drawing your line, you're basically sort of doing the same thing. You're trying to fit a line that gives you the smallest errors between the points and the line, gives you the smallest distances. So that's really all it is that you're doing. Okay. Right, so that's pretty much it. So, any questions? I imagine there's got to be a couple questions. There's a lot for you. There's a lot to do, but like you don't have to do it all tonight. Let me drag this back up so I can see you guys. There we go. All right. So any questions? Oh, can you use an iPad? Yes, you can use anything you like. If you have, you can use your phone, you can use a tablet, you can use a laptop, you can use a mainframe computer, like whatever it is, that doesn't matter. You can, if you have like a graphing calculator that does least fit linear regression, use that. That's fine. I don't have a scientific calculator, so don't ask me how to use one. So I just have an old solar powered thing with big buttons on it. But yeah, you can use Google. Google Sheets or Excel are basically the two ones I'm used to using. But yeah, so what do you have on your iPad? You're just going to go to Google and use it that way?
No, I have like an application that has like graphing paper on the app, so it's like nice. But I just wanted to make sure that's like.
Oh, so for the hand drawn one, yeah, if you're going to be drawing it by hand, yeah, you can do it on a pad. I don't want the computer to do the plotting. I want you to do that.
Oh,
So,
no, yeah.
Yeah. So if so yeah,
Or
I
should
mean,
I
I guess
just use
you
paper?
could draw it on a tablet that way, but just don't have the computer do the plotting. You do the
Oh
plot.
no, yeah, I don't think it does the plotting. I would have to like actually like write everything down or like plot everything down.
Okay.
But I mean, I can also use paper if it like makes you feel better.
No, I mean, I'd be curious to see what that looks like, but I don't, can you like freehand the plot? I think it'd just be
Yeah, I
easier
can.
to be, yeah, I mean, you can try it. It just sounds like it'd be easier to do with a, ruler and a piece of paper, but any way you want to do it, that's fine, as long as the computer
Okay.
doesn't draw it for you.
No, yeah, okay.
Yeah, no worries.
I have a
Elizabeth?
question.
Oh, sorry. Go
Oh,
ahead.
yeah. We'll get right to
It's
you,
okay, go ahead.
Lorenzo. Who is that?
Oh, it's Lizelle.
Oh, Lizelle, how you doing?
I was just Hi. I was just wondering in terms of precision, I'm sure like we want to be as accurate as possible. But let's just say we were off by a few numbers or so on
A few
on
numbers, but
something on the graph. Do we still get partial credit, I guess, for
oh, of
the
course. Oh, of course. Yeah, of course. Yeah, I mean, no one's going to be able to, you're never going to be able to draw this as well as a computer can, right? The whole point is, can you draw it? Basically, can you do it carefully? Can you take some time? Because a lot of the time I've seen student work that was like obviously done in like 2 minutes and without even a ruler or anything, and just quick line, and it's like dots, and it's like obviously that person doesn't really care much about about their data, or they're interested in the class. If I've seen you've taken some time and care, and if you're a little imprecise, not really going to care. Yeah, just as long as I've seen you've made like a real effort, that's the main thing. Because let's face it, we're not going to be drawing very many graphs, right? We're going to be letting the computer do it. That's what the computer's for. Oh, yeah, Lorenzo, you had a question.
I was wondering if I was just gonna kind of use the PDF itself to kind of mark it up and
Yeah.
just screenshot that and turn them. Is that all right?
Perfect. That's even better because, yeah, you can edit that PDF, right? I think if you have fully functional Acrobat, that's what I want you to do. Believe me. I don't, yeah, if you're printing something out and then drawing on it with crayon, yeah, that's no good for anybody. But yeah, typed in, perfect. That's exactly what I would want you to do. So good work. Yeah, is everyone able to do that? I also have Word versions of these things if you'd rather have Word. So if anybody wants the Word version, let me know. I can just post the Word versions too. If people are, because I know that the PDFs can be difficult to edit sometimes, and Word versions are much easier. So if you want the Word versions, I can post those in Canvas as well. Would that be helpful?
Yes, please.
Okay,
Yes.
no worries.
Professor, I do have a question when it comes to in one of the questions on the last activities, it was talking about the y-intercept and why it's
Mhm.
important to make it 0. Is that more for like the comparison aspect? When it comes to
Basically, I want you to explain to me why we bothered doing that. Like, why do we go through all that trouble of, writing scripts and swearing and making mistakes? Why did we bother doing all that? What was the point? You remember what the point was?
like to check the accuracy of our work, right? And to see how close the slopes are.
Mm-hmm. But
And
why?
For the corrected.
Why is that more accurate? It's based sort of what I'm getting at. You can say that, yeah, we did it to be more accurate, but basically the question then would be, well, why is it more accurate?
Because the computer is plotting it versus us.
No, but why do we bother tell the computer to do that? Is the thing. Yes, it sort of gives us a more accurate result. But why is changing the intercept to 0 more accurate than not having it be 0? Is the basic question. Yeah, it's a head scratcher, right? Yeah, I want to see what you think. So I'm not going to tell you. I actually did tell you a little bit earlier.
Okay, thank you, Professor.
Okay, no problem.
And
Professor,
oh,
Yeah.
go ahead.
quick question. So do we still need to input the R2 value or?
If it doesn't
the-
say to do so
Yeah.
on the report, you don't have to. But if
Okay,
you want to, that's fine.
okay.
Yeah. Because that's something that when you're plotting your own data, when you're collecting your own data from experiments, that's something that you're going to want to pay close attention to. Because if your R squared is like, 0.8 or something, then you may want to repeat the experiment, or you may want to leave out something we call outliers. Does everyone know what an outlier is? Should we look at that real quick? Have you heard that phrase before, an word before, an outlier? Is that new? See, no? All right, so what is an outlier? So if I'm plotting my little plot here, and I've got my, let's say I am plotting temperature in Kelvin, and I'm looking at volume of a balloon in liters. So when you heat up, if anyone's ever noticed that if you leave a balloon in a hot car, what happens to it? Anyone ever done that?
It'll pop.
Sometimes it pops, right? It gets bigger. That's because the gas molecules start moving around faster, and they take up more space as they're. So if I'm looking at and we'll learn this when we look at the gas laws a little bit later. As the temperature goes up, volume goes up too, as long as the pressure stays the same. So let's say I'm doing an experiment and I've got my balloon and I'm measuring the volume of the balloon and I'm increasing the temperature. So here's my first point, and then here's my second point, and then here's my third point. It's like, oh, it's looking good. Here's my fourth one, and then there's my fifth one, and then there's my sixth one, and there's my seventh one. So I'm looking at this and I'm going, man, these are perfect, and they go right through zero. But when I plot this on the computer, it gives me something like this. And the R squared is like 0.82 or something like that. Well, there's an obvious problem here, isn't there? What's the problem?
The outlier, the one off.
This is an outlier. An outlier means you screwed up. That's all it is. You screwed something up. And hey, we always screw something up. That's why every experiment I did in lab, I did in triplicate. Why? Because if I got an answer of 2 and an answer of 2 and an answer of 14, well, then I know that this one, I can ignore that one because I screwed that one up, and that my answer is probably somewhere close to 2. But if I just did duplicates and I got 2 and I got 14, I'd have no idea what to do with that. Is it an average of 2 and 14? Is it 2 or is it 14? Is it closer to one or the other? I have no idea. But if you do things in triplicate or in quadruplicate, you get an idea of which one of those replicates did you screw up. And believe me, I screwed up a lot. So this point right here is an outlier. Oh, go back, undo. This point is an outlier and it needs to go. So basically I just throw it out. No harm, no foul, because I have all these other points. I've got 1, 2, 3, 4, 5, 6 other experiments I've done, and those all agree perfectly. So now when I do my linear fit, it's perfect. And now my R squared is probably something like 0.98 or something. It's really, really good. And so that's how by plotting, you can identify what an outlier is. You can get rid of it and completely be able to justify it. So that's why looking at the R squared is important. Now, if my data just was garbage all over the place and I had points everywhere, then I just have to redo the whole thing. But if I have a whole bunch of results that fit perfectly and one of them doesn't, then yeah, just chuck it. There's no shame in that. Scientists do that all the time. In fact, that's why we do things in replicates. That's why you never do an experiment once, ever. You always repeat them at least twice, usually 3 or 4 or 5 times, just to make sure you've done it properly. All right, any other questions?
I have one, sorry. Oh, sorry. You can go.
Just real quick, you post these Zooms on Canvas, right?
Mhm.
For the recording? Okay.
Yes, they will be on Canvas. They go to YouTube. So I record them, I edit them, just chop off the first bit of my babbling, and then post them on YouTube, and then put the link on Canvas. So you can either just go right to the YouTube page and just like look around, or the link will be there on Canvas. They're usually up by the end of the week, usually before. If I have more than one class by the end of the week, I just have you guys. So I usually get them up pretty quickly. Oh, Talia, did you have a question?
Oh yeah, sorry. So one of the questions on the lab, it said like write or something like with the correct equation.
Mm-hmm.
Is that the one where the y-intercept is 0? Yeah, okay,
Precisely.
I just wanted to make
Yep.
sure. Okay.
That's why we
Okay,
went through
thank
all
you.
that terrible pain and anguish to do
Yeah.
that. So we can.
Okay, and we're never going to like plot that?
You
or
are
are
going to
we?
plot that.
Oh, we are? Okay.
Yeah. Because you need to show me what your results are. Are they going to be the same as mine? They may not be the same. I may have deliberately made a mistake on mine, so you can't use the results. So you want to make sure you do it for yourself. I do evil stuff like that all the time. Any other questions? This isn't the usual way we do things. Usually we're actually doing an experiment together. So it's really important that we're all doing it together at the same time. But something like this, you can do it anytime you want. You're not going to be, gargling with sulfuric acid or anything like that. So if you want to do it tonight, you can. If you want to do it tomorrow, if you want to do it over the weekend, whatever. But this is the best time to sort of, if something in here confuses you, this is the best time to ask. All right, everybody good?
I have one.
Oh,
Sorry,
yay,
one more
Lisa's got
question.
one.
It's Lizelle again.
Sorry,
So
what
just
was it?
thinking about, so when, so if we didn't have a scanner, because I know that there's certain like programs on your iPhone where you can take a picture of something, but is that accurate enough, like to show like, our work?
Oh
that
yeah,
way?
of course. Oh my
And then just
God, a
upload it that way?
scanner. Jesus, who's got a scanner? Yeah, no, just to click. And there's lots of, like you said, there's lots of apps you can get. It's software that just take that and convert it directly to a PDF. So yeah, I'm not smart enough to figure that out yet. I still, convert it to a JPEG or whatever, or a GIF or something. Basically, like put it in PowerPoint, and then I'm just, I'm old school. But yeah, if you just take it right to a PDF, that's probably the quickest, easiest way to do it. All right, anything else? Everyone's cool going forward from here? All right. Hope to see more of your faces next week, because Because remember, we're actually going to be doing an experiment next week. So I want to make sure you're not setting yourselves on fire or anything, okay? Okay. All right, man, so much quiet. Wednesday crowd is rambunctious compared to you guys. Oh, I will have a couple more ad codes coming in. There's a few people have a few more people have dropped. So any of you looking for an ad code, I think for this group, I think there's one, possibly two more. With the other group, I think there's like three more. So patience, and you shall be rewarded. Okay. Have a great weekend, everybody.
Same with you.
And
Thank you,
Monday,
Professor.
one thing I wanted to point out before we go, Monday, having office hours at 7 p.m. because it seems like that was sort of the time people wanted. And, you know, hey, I don't need time with my family either. So 7 o'clock, and we'll go over the worksheet from last week, since we only got through like the first two questions, and there's like 4 more. So we'll spend most of our time just doing that. So we'll all come together and go through it as a group. Okay. So 7 on Monday.
Professor, I do have a question for
Oh, cool.
office hours. What about for the folks that don't have that slot available? Are you available any other times as well?
Yeah, just send me an email. I can set something up for you.
Got you.
Yeah.
That's
Yeah,
it.
no worries. Yeah, that just seemed to be the best for because I asked, like, you know, what about mornings? Everyone's like, no. What about afternoons? No. So it's like, all right. So it was either going to be Monday night or Friday night. Nobody wants to do chemistry on a Friday night, you know, unless it's ethanol research or something. So we're not going to do that. Anything else? I think there's one more question there.
Is there a Zoom specifically for that?
Yes,
For those
there
office
is.
hours?
And I think it's in the announcement. I think I put it in the announcement. Yeah, I think it's in the announcement. And if it isn't, it is in, I was sorry about putting I sort of hid the Zoom links in you guys. So it's like bad professor. So I took them out and I put them in their own place. I think it's like the second link in the very first module in Canvas. Basically says, these are Zoom links. I am sorry. So they're right. So it's the Zoom links for the meeting times, the lectures, the labs, and I'm pretty sure the office hours are in there too. And if they're not, which they're probably not, I will put them in tonight. Thanks for reminding me. Okay. Anything else, folks? Remember, if any time you have like a question, as you've seen, if you sent me an email, I respond to them fairly quickly, unless I'm out, you know, walking the dogs or something. So, and if you want to set up a face-to-face, we can do that pretty much anytime. Okay. All right. Have a great night, everyone. I'll talk to you soon.
Thank you.
Bye, everyone.
All right. Bye.
Thank you.
Thank you,
All right.
Professor.
See you later.